Hello everyone. We are very pleased to be here today to present you our company, Pasqal. We are Loic and George, respectively CTO and CEO of Pasqal. Pasqal is a hardware company building quantum processors out of a neutral atom technology. This technology has been underestimated, and today I would like to change this vision. Very recently, IBM unveiled their last processors, hitting 127 qubits. That's very impressive, of course. But come on, neutral atoms already hit 200. At Pasqal, we have these numbers at the industrial level, and in the lab, we already have 500. Our plan for the next future is to deliver this potential on the largest possible scale. Our plan for the next 2 years is to deliver it, to push the technology further, improve the fidelities, improve the number of qubits. At the same time, we are also a full software stack company devising applications that leverage the strength of our processors. To do so, we raised 40 million euros. We have a team strong for 17 people with more than 10 nationalities represented in the team. And we already partnered and have customers, one of the largest corporates in the world. Not surprising that we've been awarded the title of Startup of the Year. In this presentation, in the first part, we will introduce you the technology. We will also give you where do we stand right now. And finally, we will give our vision for the future and share a couple of breaking news at the very end. Now, I leave the floor to Loic, who will introduce you the technology.
Generally speaking, our technology is all about controlling individual atoms with laser light. And everything happens here, in the vacuum chamber that you see on the left. In this vacuum enclosure, we can place individual atoms in arrays of so-called optical tweezers. An optical tweezer is essentially a trap for one single atom. You cannot have two of them in a trap, only one. And the great thing about this technology is that you can reconfigure the geometry of the array of qubits at will. Using standard holographic techniques, you can do that in 1D, 2D, and even 3D geometries. Here, each green dot corresponds to one unique rubidium atom. And so with 72 atoms, we're able to do this small Eiffel Tower. So our qubits are atoms. And the computational states of our qubits, the zeros and the ones, they correspond to different energy levels of those atoms. And to create entanglement in our system, we use specific states which are called Rydberg states. You can have a classical picture in mind for those Rydberg states. The outer electron is orbiting far away from the nucleus, and this generates a dipole with a minus charge close to the electron and a plus charge close to the nucleus. And if two atoms are brought in a Rydberg state at the same time, then they will interact. And this will create entanglement in our system. So that's how our technology works in a nutshell. We use laser light to trap atoms and to manipulate their quantum states. Using specific states, we generate entanglement in the system. And the great thing about using atoms as qubits is that they are all identical. You don't have to manufacture them because nature does that for us. And last but not least, everything works at room temperature. We don't need cryostats. It took us almost 20 years to reach that point, and Georges will tell you about the key milestones that we've hit along the way.
With great pleasure, Loic, this will bring to mind very happy memories. It all started at the dawn of a new millennium with two scientific breakthroughs. The first one was a theoretical one. Lukin and Peter Zoller brought the idea of using this Rydberg interaction to make the atom interact at large distances. That's the first building block of a quantum processor. The second breakthrough is experimental. It happened, strangely enough, the same year, in 2001. where we got the first evidence of the signal of a single atom in an optical tweezer. Before this breakthrough, people didn't know how to manipulate single atoms without changing their quantum behavior. Merging the two is very challenging. Optical tweezers were known to be very good atomic traps, but loaded with hundreds of atoms. The first signal happened during my PhD thesis. Sorry. The two of us, Nicolas Schlosser and I, were working late at night in the lab of the Institut d'Optique, looking at the signal on the computer. We've been seeking this signal for months, fairly convinced that the tweezer was loaded with tens of atoms. That was too much, of course. So we decided to reduce the number. We cut the magnetic field, we cut the atomic source, and the signal went down. And suddenly, we could see that on the signal, steps. And this is a clear evidence of an optical tweezer either loaded with one and only one atom or with zero atom. A third step that would signal the presence of a second atoms in the trap never occurs. At the same time, we could see on the camera, the picture you see here, that the pixel which is imaging the optical tweezer, the one in red, was blinking as the atoms were entering the trap one by one. That was fascinating, mind-blowing, and to be honest, totally unexpected. But still, the signal is indisputable. Should I point out that this discovery happened in the exact same labs, on the exact same optical table than 20 years earlier, Alain Spey demonstrated experimentally the reality of quantum entanglement? Here is a picture of Alain Spey in the lab on the famous optical table. And today, I'm very pleased to have Alain Spey as a co-founder of Pasqal. In 2009, Antoine Brouez, another co-founder, implemented experimentally the idea of Michel Lukin and Peter Zoller. What he did is put two atoms in close proximity, a couple micrometers away, and shine a resonant laser onto them. In this regime, the Rydberg interaction prevents the simultaneous emission, the simultaneous excitation of both atoms, generating entanglement. In this study, Antoine demonstrated that this scheme was indeed efficient. In 2021, he pushed things further. Building a setup with 200 atoms, he was able to study the dynamics of the Ising Hamiltonian, which is the iconic model for magnetism. He studied the dynamic at a scale which has never been done before. In parallel to this program in this progress in the field of quantum simulation, other groups were working on improving the fidelities, implementing the gates. That's the era where the technology was struggling the most. But as you can see here now, we are catching up. The fidelities are improving thanks to the work of Safman, Lukin, and Andres. So the technology was underestimated, but now things are changing and rather rapidly. Just this year at Q2B, and for the first time, you've been able to listen to 3 talks by a neutral atom company, Quera and Qualcomm on Tuesday, and today Pasqal. And I know that the fourth one, Atom Computing, is in the audience today. At the same time, the Boston Consulting Group, in its last report, put neutral atom on the map, underlying the superior qubit numbers, while having some other metrics. And this is not too good to be true. Just this year, 2 papers published in Nature hit the 200 qubit mark by Michel Lukin and Antoine Brouez. And this is an interesting story too. In 2019, Antoine and his team were working with 50 atoms. They were expecting to reach 100 by 2020. And finally, they reached 200. In fact, during the first lockdown, when the COVID crisis hit, the lab was closed, and the experimentalists couldn't have access to the experiment anymore. So they work on the classical algorithm that were controlling the hardware. And this is this improvement which led to this great result. And to me, it really shows the power of the technology. working a couple months on classical algorithm is enough to double the qubit count. Talking about software, Loic, I'm sure we will agree that a good hardware is useless without good software. So if you mind talking about our strategy regarding these aspects?
Yes, sure, Georges. One of the key differentiators of Pasqal is that we are not only building the hardware, but also the software suite to pilot the hardware and address applications. And we have partnerships with end users, both in the academia and in the industry, to study real-world problems. An example is that we are working with a major utility company on a problem of smart charging of electric vehicles. They have the knowledge in terms of smart charging, while we have the knowledge in terms of quantum computing. And together, we can find the optimal solution to their problem by combining our expertise. That's a really fruitful development cycle. We get to improve the software so that it better addresses the needs of the client, but also we get to understand what would be the hardware features that would lead to better solutions in the future, so that it helps us developing the next generations of the hardware. That's why we decided that a full stack approach was the way to go at Pasqal. And another advantage of being a full stack company is that we can devise applications that are well targeted to our hardware. That's because we know very well what are its weaknesses and what are its strengths. As I told you earlier, one of the key strengths of neutral atom processors is that you can control the geometry and vary the geometry from shot to shot. And this feature enables us to encode data under the form of graphs into our processor. The nodes of the graph correspond to atoms, and the edges in the graph to atom interactions. And with this encoding, you can apply machine learning procedures on graphs. So that's what we proposed earlier this year, to do classification or regression tasks on data which has the form of graphs. Let's illustrate that on a particular example. It's an example in biochemistry. Given a certain compound, the objective is to be able to classify its reactivity. Is it harmless or is it dangerous? You have an example of such compounds on the screen. As you can see, they have an intrinsic graph structure which can be well represented on our hardware. Here, each bright dot, again, corresponds to having one atom. So that's the initial step. And then you apply a quantum dynamics to the system and you measure the system. And of course, the outcome of the measurement will depend on the input graph. And the objective is to be able to find the best quantum dynamics that is able to differentiate the harmless compounds from the dangerous compounds. So we do that during a training phase where we supply to the algorithm compounds and their known reactivities. And we try to find the optimal quantum dynamics that is able to efficiently separate between the two categories. So that's what we did on the hardware. And here are the results on a test set. In a test set, you only provide the compound and look at what is the prediction of the algorithm, and then you see if the algorithm was right or not. Here are the results that we obtained over the past few weeks on the hardware. In 63% of the cases, the quantum evolution kernel, the procedure that I told you about, was able to correctly classify input data. And this compares favorably with respect to classical methods. So we have around the same accuracies. But this is only the beginning. We will continue improving both the hardware and the software, the algorithm, and we hope to achieve even better results in the future. Those are preliminary results obtained on the hardware over the past few weeks. And this really underlines that having a great programmability in terms of the position of the atoms allows you to tackle new use cases. If you wanted to do that on other platforms, you would have a hard time. Doing that on trapped ion quantum computers, you would need 10,000 more quantum operations to do that. On superconducting quantum computers, you would need 20,000 more operations to do that. So it's simply out of reach with current versions of the devices that we have right now. So this use case was invented by Pasqal, published earlier this year in this paper, Physical Review A. And it was implemented on Pasqal hardware by Pasqal engineers. And speaking of engineers, Georges will now tell you about our plans to take the tech out of the lab and into the field.
A very impressive result, Loic. And now that we are all convinced by the efficiency of this platform, the challenge today is to deliver it on the largest possible scale. Today, there are already existing products that are built on the same building blocks than our processor. One can think, for instance, for atomic clock, which are used in GPS, even in space, or atomic gravimeter that are now reaching exquisite sensitivities. Our processors are using only off-the-shelf components. All we have to do to bring the technology to the next level is to engineer it. We do not need nor scientific breakthrough nor industrial breakthrough. At Pasqal, we have a team of engineers whose mission is to devise robust and reliable processors that are operational 24/7. In only 2 years, we were able to move from this setup, this chaotic system, typical of an academic neutral atom experiment, from this fully racked system that you can see on the right. We simplified the setup. We use standard industrial method, breaking down the system into subsystems that are independently aligned and finally brought together. Here is a short video showing you how we managed to do that.
Quantum information processing offers a new paradigm compared to the way information is processed on a classical computer. And it has opened so many new perspectives over the past years in such a broad range of applications that there is now a strong need for reliable quantum processors that can be remotely operated 24/7. At Pasqal, we have launched a new product line called Fresnel that precisely addresses this need.
The Fresnel quantum processing unit is an assembly of about 3 by 1.5 by 2 meters divided in 3 parts. Lasers and electronic modules are located on easy access racks for integration or maintenance purposes. The quantum core at the center is also modular itself. The atomic sources, the laser beam shaping and imaging systems are assembled on independently mountable benches, allowing easy transportation, part replacement, or design upgrades.
Inspired from the first Pasqal prototypes, the Fresnel architecture has been fully revisited to comply with industrial requirements, modularity, reliability, and full remote control.
In order to make our technology accessible and practical today, we are building a quantum computing as a service offer. Through our cloud platform, users can have on-demand access to our self-hosted quantum processors. Using our software suite, anyone can write quantum programs, seamlessly run them on one of our machines, and integrate their results with the rest of their stack.
We expect to deliver the first Fresnel product on cloud access from Q1 2022 and a second one from Q3 2022. Moreover, we're setting up a new building dedicated to production, where we want to first improve our integration process and second, increase our production rate. So stay tuned.
Impressive, isn't it? And once again, this is doable because we are operating at room temperature. We don't need these complex cryogenic systems, and we don't need to manufacture the qubit. I want to give you a number. If you were to build this setup in academia, it would take something like 2 to 3 years to build it, because it will be built by PhD students. At Pasqal, to build our first benchtop setup, it took us only 1 year, because it was built by seasoned physicists. For the rack system, it took us only 6 months. It is now being assembled by engineers. And for the next generation, we will reduce that time down to 3 months. Loic, it seems like we have our first product, reliable and powerful enough to go to market. But my feeling is that we can do even better with neutral atom.
Absolutely. So as Georges just explained, and as you saw in the video, we already have an industrial device working in the range of 100 to 100 qubits. But with the exact same hardware components, we should be able to scale the system up to a few thousand qubits. It's because we don't need to change the hardware to do that. An example is that for generating the array of qubits, you only need one laser, whatever the number of qubits, so that you can scale that up by improving the quality of the experimental procedures. But it's not only a roadmap, we've already started doing it. And here, you can see that we have today 500 qubits already available in our prototype. But that's not the end of the story. If you want to go to the regime of quantum error correction at scale, then you need millions of high-quality, well-connected components. And for that, we will be needing to change the architecture. We will continue working with atoms, with arrays of atoms, but then we will couple them to photons at the single particle level as well. And that way, we will benefit from both the nonlinearity of the atoms and the high coherence properties of photons to propagate quantum information. We will be benefiting from the advantages of quantum optics on the one side and atomic physics on the other side to reach that goal. And to help us achieve our ambitions, we are happy to announce that we have signed a new scientific advisor, Professor Nicolas Treps, from Sorbonne Université and Kastler-Brossel Laboratory. He's one of the leading figures in quantum optics, and he will help us achieve our ambitions.
And that's not all. Today, I'm very pleased to unveil our partnership with NVIDIA. We just received a pod of GPUs we ordered from them, and that will strengthen our emulation capabilities. This is one of our key commitments to offer to the end users the best tool on the entire value chain. And this GPU pod will strengthen our emulation tools, which is a key feature to develop new applications. And stay tuned, we will also unveil, beginning of next year, a strategic partnership with a leading software company as a commitment of being a full software stack company. As a wrap-up, I would like to remind you our strong conviction that neutral atoms are the next quantum leap for quantum computing. 200 atoms at 200 qubits at the industrial scale, 500 in the lab. And Loic is a climber. I'm also a mountaineer. And when I have a look at your progress, I can't help but draw parallel between this progress and the strategy that was first used to reach the summit of Mount Everest. The first attempt the climbers did were on the North Ridge, because the path is easy in the beginning, allowing the climbers to reach high altitude rather rapidly. But at the end, just before the summit, there is a bottleneck, which is almost impossible to climb, or at least it was impossible to do so at that time during the first half of the 20th century. So people will keep trying, but without success, being stuck just at this point. It came as a surprise that the successful path was actually on the South Ridge, where the difficulties lie in the very beginning of the climb. But when you think about it, that's the perfect strategy, because the climbers are not yet exhausted by the lack of oxygen. So they can overcome the hurdles. And once done, the path is easy and almost always successful. Our Mount Everest today is to build the most powerful quantum computer ever. And if we were to reach the summit together, we recommend to follow the South Ridge, or should I say Pasqal and our neutral atoms. The steepest part have been successfully carried out, and we now have the summit in sight. So let's join us together for the final ascent. Thank you for your attention.
Yes, thank you so much for the very nice introduction. So, like, I was wondering your quantum machine learning example. So, were you having individual addressing and digital gates, or is it more like analog fashion? And you showed there is orders of magnitude kind of speed up, or orders of magnitude easier for neutral atom system, and in this graph problem. So is this graph problem kind of universal, can be mapped to like all different types of NP hard problems, or is it a specific type of machine learning problem?
Yep, okay, thank you very much for the question. So to answer the first part, it has been implemented using the analog mode, not digital gates, but analog time evolution of the system. And so so it's a classification procedure in machine learning where we don't have direct mapping to NP-hard problems or anything like this. You can apply it to various data sets that are available out there. And the results that we have right now is that we are not overperforming by a lot the other methods, as you saw on the plot. But the objective is to try to see if we can scale better and if we can reach even higher accuracies.
Thank you for your talk, very impressive. So I also love climbing mountains. Maybe we can start in the Mont Blanc. So it seems you're pretty fast in scaling up these numbers of qubits. So what is limiting, or what is hard about scaling it up? Because it all sounds so easy almost.
It's really an engineering problem. I mean, to reach the first level of scaling, I mean, building these industrial devices in the 1,000 qubit range, it's only a matter of engineering. It's not that easy. I mean, we know how to do. Engineering means that we do not need scientific breakthrough. It doesn't mean that it's an easy path, but we know how to do that, as it was shown during the video. And of course, the next challenge, if we want to scale even better, to reach millions of qubits, to change the architecture, of course, this is R&D. But we are also engaging in this path as well.
But is it mainly on how to control? You're using one laser to address the total system?
Yeah, that's the reason why it is so scalable. You know, once you are able to manipulate one atom, you just need to multiply the system, basically.
Interesting. I'd love to learn more.
You did show some digital gate fidelity numbers. Is that representative of all possible pairs of atoms in your 200 qubits?
Yeah, I mean, the fidelity numbers now, they are higher than 99%, so catching up the best state-of-the-art fidelities, and it is on the higher, on the entire array. As I was mentioning, I mean, it's not the limit, we can do better, we are improving. I mean, the physics is well understood, and we know what to improve to go even beyond that.
Thank you.
Okay, let's thank the speakers again. Thank you.